So I'm going to talk about work that perhaps started about 5 to 7 years ago when I came up with a radar design for a completely different application for studying the ionosphere, upper ionosphere. And that's what I do. I mean, my background is in inverse problems and in space physics, and I do interdisciplinary work between both of those two topics. So I do statistics and a lot of linear algebra. And this work is work that got started when Koki invited me to come to Kuhlensborn to develop a new type of a meteor radar. And this is a meteor radar which hopefully I'll be able to convince you that is a useful idea. And also I'll be able to probably communicate to you that meteor radars are actually not used to primarily observe meteors. They're used to observe mesospheric wind. These are my collaborators. Hopefully I have not forgotten anyone. If so, I'm sorry. This is a simulation of a wind field that just I have used nothing else than just frequency to minus 5/3, which is the Kolmogorov spectrum of energy for turbulence. But it kind of looks like cat fur. But this is what we're trying to measure and characterize. We're trying to characterize the wind field in the mesosphere. So what is the mesosphere? I looked at the titles for the speakers, and I figured that I probably might be a good idea to put one slide here to explain what is the mesosphere. So the Earth's atmosphere consists of different layers. Troposphere, which is probably the most important one for us because that's where we are and that's where most of the atmosphere is. There's the stratosphere, and then there's the mesosphere between about 50 and 100 kilometers. And most of you might not even be aware of something called the mesosphere. But it happens to be what this institute actually focuses on, mostly, studies of the mesosphere. Eric Becker will probably tell you why it's important to study this region in his next talk, and we'll be able to elaborate a little bit more about this, but as a little bit more of an outsider to the mesospheric science community, I know that this happens to be the boundary between boundary of space. So at about 100 kilometers, aerodynamically, airplanes can't fly anymore. That's the definition of space. It's also a place where atmospheric waves are amplified. I mean, tidal waves have a 1 centimeter per second velocity at ground level, but they can be 100 meters per second in the mesosphere, and these waves also break there. There are a few things that we can observe, and it's an interesting region because it's very, very hard to observe. We can't fly an airplane through this region. We can't fly a satellite because there's not enough lift, but we can't fly a spacecraft because there's too much drag. We can't really do any in situ measurements. We can do sounding rocket measurements, but those are one-off measurements, and they cost about $1 million each. So primarily, this is we use different remote sensing techniques. We use lidars, we use radars, we use spectral measurements of the mesosphere from space and from the ground. And I'm going to be talking about one of these radar measurements. Here's a picture of the mesosphere. I saw this picture a few years ago. It was taken by an astronaut on the International Space Station. It's really cool. This shows the Earth's atmosphere. This is at about 100 kilometers. You can see this green air glow. That's 5577 angstrom air glow from atomic oxygen. And right below this green layer is the mesosphere. So it's a very thin layer, which kind of marks the upper boundary of our atmosphere. And you can see here a meteor that's burning up in the mesosphere. So meteors, they burn up in the mesosphere because that's where the atmosphere starts to be dense enough that ablation occurs and meteors get destroyed there. So that's one optical phenomena that you can see that occurs in the mesosphere. Another optical phenomena that you can see that occurs in the mesosphere is noctilucent clouds. Has anyone seen noctilucent clouds? A few people. So if you look at the right season towards the north, August, September. What's the right season? Is it about that? June, July. You can see them at night towards the north. It's occurring. I live in Tromsø, so it's occurring right above me. I can't really see them because we have 24-hour daylight. But these are clouds in the mesosphere, which are scattering of sunlight from icy dusts in the mesosphere, and you can see that it looks like it's turbulent. All right, and you can even look at these clouds from satellites, and you can see that there's a lot of dynamics that occurs in the mesosphere. Okay, so why did I get involved in this? This is maybe my explanation after the fact. Mesospheric, because it's very difficult to measure, we don't have a lot of measurements between spatials of the distribution of kinetic energy between approximately this spatial scale and that spatial scale. So between 1 kilometer and 100, 200 kilometers, we don't have a lot of information about the kinetic, about the dynamic, or the kinetic energy distribution of mesospheric fluid. And we wanted to improve that. We wanted to come up with a new technique for bridging this gap and making this measurement. Okay, I already listed this. There are methods for measuring the mesospheric wind. You can use rocket experiments. You can use lidars, spectrometers to measure Doppler shift of spectral emission and absorption lines. You can use radar scattering off of ionospheric irregularities in the mesosphere using very low frequency radars. You can use larger radars like the Marsi radar that IAP Kulenborn operates in Andenes in Norway to look at weakly ionized turbulence, scattering from weakly ionized turbulence. You can even use radar scattering from ionospheric plasma without turbulence. You need very large electron densities, and you typically only see this when you have at high latitudes when you have auroral precipitation. And finally, this method that I'm going to be talking about today mostly is radar scattering from meteor trails using VHF frequencies. These are frequencies between 30 and 50 megahertz. And all of these different methods have advantages and disadvantages, and I think the advantage of this method is that it is very useful for measuring between these two different scales of the energy spectrum. So that so KH here this is a horizontal wave number. So that would be 10 to minus 5, which corresponds to 100 kilometers wavelength, and that corresponds to 10 to minus 2. So that's 1, 2. So that would be 100 meters, 100 meter wavelength. Right. What does a meteor radar look like? This is what a meteor radar looks like. I'm used to working with large radar systems like Arecibo or Hikamarka or IceCats. They're 300-meter antennas. One thing that I really find cool about meteor radars is that it's just a bunch of small antennas. They're very inexpensive. You can put them on your backyard, and you can build a meteor radar, and you can measure 100,000 meters per day with it. This one is in Neustrelitz. These are the reason why there are multiple antennas here is in order for a meteor radar to work, we need interferometry. We need to determine where the meteor echo comes from, and we do this by measuring the time of arrival of the echo between these different antennas. Okay, another critical ingredient for how a meteor radar works is meteor radars measure primarily something that's called specular trail echo. So if you have a meteor that's flying through the atmosphere, ablating, leaving behind a trail of increased electron density. This is a radar reflector, but it only has a large radar cross-section if the incoming radio wave and the outgoing radio wave are organized in such a way that the Bragg scattering vector, which is the incident K vector minus incident K vector plus scattered K vector, which is this K vector here, is perpendicular to this trail. So it satisfies this specular condition. In that case, we get a very large radar cross-section, and we can measure them with these small radars. And what we measure is a one-dimensional projection of the neutral wind. So when this meteor trail is formed, it's not moving at the velocity of the meteor, it's moving at the velocity of the wind, because you leave behind an ablated trail of increased electron density, and that drifts along with the neutral wind. But with a meteor radar, when we measure the Doppler shifts of this kind of transmit-receive path, we measure a one-dimensional projection of the three-dimensional mesospheric wind. And that's given here. So R would be a measured Doppler shift, and that's K dots V, and V is the mesospheric neutral wind, which we want to measure, plus some measurement noise. We always have measurement errors. And it's customary to use UVW as the three different components of the neutral wind. Right. Okay, so question. So if this is all you knew about meteor radars, how would you go about improving the meteor radar method? Any ideas? More power rights, that would be a good idea. Bigger antennas. What else? What would be like a clever way of improving it? So the critical point is that we only see meteors if they satisfy this condition. If we have a meteor that's like this, oriented like that, we would not see it with this transmit-receive path. Any ideas?
Statistics about the direction of the neutral light?
What?
Statistics about the direction of the neutral light?
Sure. More transmitters and receivers. But you cheated. You know the answer. So yes, but you were kind of right too. I mean, if we build more transmitters and more receivers, more meteors will satisfy the specular condition. And this is what Gunther Stober and Koki Chai realized a few years ago. And they said, what if we build this kind of a network? We have a combinatoric advantage. If we have multiple transmitters and multiple receivers, each transmitter and each receiver has a unique path, and that can and then we almost get a completely new set of meteor trails, and we can increase the number of meteor trails that we measure. And if we increase the number of meteor trails that we measure, we get more information about the neutral wind. And the same technique is also used for astronomical purposes. The Seymour radar in Canada is based on a similar principle. And so, yes, we get a lot more meteors just by adding antennas, making a network. And this is where I got in. I mean, the radar that I had developed is kind of like GPS. It's or CDMA, like cell phones work. Instead of sending out pulses, sending out Dirac deltas, I send out noise. And I designed a radar which allows, and I already designed this radar for another purpose, but we applied it for meteor radars here, where the radar transmits with multiple different antennas operating on the same frequency, but each one of them transmits a different pseudorandom sequence. And the advantage of this is that, first of all, we get a lot more average power outs. We can also disambiguate different transmitters on the same frequency. And this is a project that was a joint collaboration. I was still at MIT when I got this funding. But this lasted. We just concluded this project in 2018, and it was a very successful project where we worked on this radar. We're not doing any magic. This is, again, like I said, this is a technique that's already used for GPS and it's already used for mobile phones. I'm pretty sure militaries use this kind of radars. We use modern signal processing methods, basically linear least squares, compressive sensing ideas, which is just coming up with the sparse bases. And for meteors, it's easy. It's just Kronecker delta bases with few Kronecker deltas. Here's the kind of the radar signal process, the basis of the radar signal processing for a multistatic radar. It's low frequency, so you have the echo doesn't change very fast. Your equation is essentially a convolution equation. So this would be the transmit waveform delayed by distance r, and this would be the echo power from range r, or echo scattering amplitude. But because we have a multistatic system, we actually have multiple paths, n, so n denotes here path. So we have a measurement equation which consists of multiple different convolutions. And our task is to solve for n, sigma n, and we typically have about 5 or 6 of n is 5 or 6. With a pulsed radar, this epsilon is a Kronecker delta. If this is a Kronecker delta, there's no way it will ever be able to solve this equation, right? There's no unique solution to it. If this is pseudorandom noise, you know what that noise is. If it's a long enough sequence, you will be able to come up with an overdetermined linear least squares problem and solve it. It's quite easy. And you can even get better results if you build a sparse model which only includes unknowns at the ranges where meteor echoes occur. And here's an example of it. This refers back to what I said about different communities not talking to each other. This is a radar signal processing technique that's still used today. This is how radar signal processing, or radar engineers typically will write maximum likelihood estimator. This is their idea of a linear least squares. And it's not right. But they still use it because for a point-like target, it is optimal. But our targets rarely are point-like, and this results in side lobes. And this is from a poster that actually will be shown by Mikael Urko today at the poster session. If we do a linear least squares estimate, we get slightly better results. We get rid of all of these side lobes, which occur because we're not properly solving the least squares equation. And if we do a sparse model, we can also get better signal-to-noise ratio and see even more meteors. So this is an example of this new meteor radar that we developed. In 1 minute, we see about 40 echoes. Other advantages of this radar is that there are no range Doppler ambiguities. If you use pulsed radar, you have all the problems that you would have with Nyquist sampling. We don't have those problems with pseudorandom noise. It's tolerant to RFI, or to radio interference. A random signal does not correlate with anything else except the same instance of that random signal. And so with a random transmitted signal will not correlate with radio interference. So that's why this radar is tolerant to radio interference. It's well suited for multistatic networks, low peak power, off-the-shelf components, open source, small and inexpensive. And more details in these two papers. And here's a picture that was taken during the last campaign by Jörg Trautner. He set up one of these antennas in a pear tree on the yard. And that's the receiver system. It's also commercial off the shelf. Other advantages of this type of radar is that it allows us to separate multiple different transmitters on the same frequency. And in addition to building a multistatic network with transmitters and receivers located hundreds of kilometers away from each other, we can also build a system where we have multiple transmitters located near each other in a radio interferometer configuration. And if each one of these transmitters transmits a different signal, we can, and we get scattering from a meteor trail echo with one antenna. With one antenna, we can actually measure signals originating from multiple different transmit antennas. And that allows us to, with a single receiver antenna, allows us to measure the angle of transmission, the angle of departure for the radio wave. So it gives us another way of determining the position of a meteor trail. And this is really useful. Koki Chow realized that this is useful because when he started building a network, he went to different places and said, can I install a 2 kilowatt transmit antenna in your backyard? And everyone said, no, no, the birds will not like it, and our kids might get hurt. Would this type of a different, I mean, now that's a traditional system, but with this type of inverse system where we have multiple transmitters transmitting different codes, and angle of departure, we can install one single passive antenna which does not radiate, which only receives, and we can determine the position of meteors using this system. So I think this is really useful for actually building a network. We can go to schools, we can go to amateurs, we can go to different people, and we can easily convince them to install one antenna that looks like this. We can't convince them to install an antenna like this if it's hot, if it's radiating 10 kilowatts or 50 kilowatts. Nobody will like that. Okay, here's a measurement from kind of a first light measurement from last summer's campaign. This was kind of a proof of concept. We showed that the method works. We got a relatively good amount of meteors. 30,000 meteors per day, I think, is actually slightly better than a normal meteor radar. Okay. I'm starting. I need one more prerequisite here. Reynolds decomposition is decomposition of the wind field into two components. So if this is a wind field, U, this is a two-dimensional wind field, it can be decomposed into a low frequency component. So this is low spatial frequencies and high spatial frequencies. There's no official definition of what this frequency offset should be. That depends on the observer, or depends on what you want to do. But it's a very handy way of grouping your signal and the wind field into a mean wind and a fluctuating wind. And they can be both studied separately. So I'm going to be using U bar as a mean wind and U prime as a fluctuating wind. Okay. Again, just to remind you that this is a radar measurement. This is a meteor radar measurement. So it's a one-dimensional projection. So the Doppler shift that we measure is k dot v, one-dimensional projection of the mesospheric neutral wind at position p. So each meteor gives us one projection at position p of the wind. How do we get information about the mean winds? This is a standard technique, the mean wind amplitude estimation. Here you assume that your wind field consists of two mean components, two horizontal components, and then it consists of fluctuating components. And when you do this, you get this kind of a measurement equation. It's the x component of k vector times u and v, mean wind, and you can shovel all of these fluctuating components into xi, into zero mean random noise. And this becomes your measurement equation now, which is very simple. And this is what goes into your noise. So all of these fluctuating components, you can treat them as noise, zero mean random noise. You get a very simple linear relationship between lots of different Doppler shift measurements with different k vectors at different positions, and then two mean winds. You can do a standard maximum likelihood estimator, and you can get a mean wind. One of the cool things with these types of meteor radar networks is that because we have so many more meteors than we have had before, instead of just estimating one mean wind vector, we can actually estimate a wind field of a vector field of mean wind. And this is a paper by Gunther Stober and Koki Chow. Oh, this is a Stober et al. So, and the really cool part is that this hasn't really been before, and this was only enabled by this realization that if we build these meteor radar networks, we get more meteors. And Gunther has a poster about this wind field inversion tonight, and he uses essentially Tikhonov regularization, where he minimizes the Laplacian to estimate these wind fields. You can also look at the fluctuating components of the Doppler shifts by subtracting, first estimating the mean wind and then subtracting the mean wind from your Doppler shift measurements. And what you get is you're only left with the fluctuating component of the wind field at that point. And now we get to the, how much time do I have left?
20.
20 minutes, okay. Perfect. Now we get to the, so these are all existing techniques. Now we get to the new contribution of this paper that we just submitted a few months ago. If you treat your mesospheric wind field like as a random process, as a stationary random process, V is a random vector, and then it's completely characterized by its second moment if it's Gaussian, and if you have velocity at time t and position p multiplied by transpose of velocity at time t plus tau, some time lag and position lag. So S is a spatial lag, tau is a position lag. You get this kind of set of 6 unique correlation functions. These on the diagonal you have autocorrelation functions of the mesospheric wind. So here you have zonal, meridional, and vertical autocorrelation functions as a function of time delay, displacement between measurements, and spatial displacement between measurements. And then you have these cross-correlation functions. So these correlation functions would completely characterize this process if we assume that it's a zero-mean Gaussian random process. So Koki had the idea that, why don't we try to estimate these? And I thought it's a good idea, and I decided to help with it. And last time when we wrote a lot of these equations, if we have 2 different radial measurements, so Ri and Rj these are 2 different meteors measured at 2 different times and 2 different positions. So they're one-dimensional projections of the mesospheric wind. UVW is included there, and the k vectors, basically the measurement geometry, is included there too. And we have measurement noise. Psi I and psi j are assumed to be Gaussian zero-mean independent random variables. If we now take a product of these two, we get all of these terms. These last 2 rows are all zero-mean. So the only non-zero mean terms here, assuming that I is not j. If I is j, then we have a problem. But in our case, I is not j. So this last term is also zero mean. Because if you multiply 2 independent Gaussian random variables, their product is their mean is the mean is 0. So these last 3 rows result in zero mean, are zero mean. So if we look at these elements here and we take the mean value, we already took the mean value here, so we know that GUU, all these correlation functions come from the different components of the second moment of this velocity. We can express the two radial Doppler shift measurements multiplied with each other as their mean value plus some random variable. This random variable is not Gaussian, but with zero mean. We can then make we can express this as a linear relationship, where we have all the 2 k vectors of the 2 different measurements, and we can stack multiple different measurements of different measurement pairs. So this would be measurement 1 times measurement 2, measurement 1 times measurement 3, and so forth. If all of them if all of these measurements have a similar time lag and spatial lag, they're all essentially, and we make the White-Sense stationary assumption of these correlation functions, they're all measurements of the same unknown quantity, these correlation functions. This is not completely new. I mean, something along these lines has been done by Denise Thorsen already in the late 90s. Wayne Hawking actually considers this type of an equation, but he only considers the case where Ri and j equals is j. So I equals j, and he only considers that special case. And Mike Nichols has also worked on this with incoherent scatter radar, But we are now applying this for meteor radars. And I think meteor radars really get a huge benefit from this method. Again, you can use a linear least squares estimate for the unknowns. This is not the maximum likelihood estimate, unfortunately, because we can't make the assumption anymore that our unknown is Gaussian, but it's close enough, and this is really a fast way to do it. We really can have millions of these measurements in a measurement equation, so we kind of have to have a fast way of solving it. Okay, what kind of lags can you consider? Here are two different ways that I think about forming lags. If this is one meteor measurement, position pi and time ti, it is giving us information about v at ti and pi, and if I make a set t0, t0, and v0, a set that includes an interval in time and space, I get a set of measurements. For each measurement in that set of measurements, I can form another set of measurements which are in some kind of a box with a spatial displacement, and that gives me a set of measurements to correlate, and they will tell me something about. They will give me a measurement of the correlation functions at that spatial lag. I can also have a temporal lag there as well. I can also do another thing. I can ignore the direction of the spatial lag. I can say that I want my spatial lag just to be horizontal distance, and this is useful especially for the mesosphere because it's very stratified. So again, this method, this matrix equation, we get one such matrix equation for one given lag with some lag resolution in temporal and spatial lag resolution. Why are these useful? First of all, the Wiener-Khinchin theorem relates correlation functions to spectra. So if we can make a temporal autocorrelation function with zero spatial lag, that's actually a temporal spectra of fluctuations in the wind. We can also do spatial spectra. If we do a spatial Fourier transform of the spatial autocorrelation function at zero temporal lag, we get a spatial spectrum. We can also do two-dimensional or up to four-dimensional correlation functions if we want to. Another interesting thing is that these correlation functions, the zero lag of the correlation functions is related to the kinetic energy in the mesospheric wind. So this has units of meters squared divided by seconds squared, and if you multiply that, the zero lags of the correlation functions with the neutral density times half, you get joules per cubic meter in kinetic energy. You can also use these correlation functions at different lags to estimate how the kinetic energy correlates in time and space. Okay, so now I'm going to show some results from the first campaign. The really cool thing about this radar that we built, which is a radar network, is that we got about 100,000 useful measurements in one day. This is about 10 times more than you get with a typical radar. So I'd consider 10 times improvement as some kind of a yardstick of success. So I think it was a really useful thing that we did. All of these points indicate locations of meteors measured over 24 hours. And just to demonstrate, I have some plots with 5-second intervals. So this is the first 5 seconds. We have two different meteors. There's one meteor here and one meteor here. These are all the stations that we had in our network. This is the next 5 seconds, so 3 more meteors. Next 5 seconds, 3 or 4 more meteors. We just keep getting meteors, almost 1 per second. And every time we get meteors, for example, if I assume that 5 seconds is simultaneous in terms of mesospheric winds, I can now use these two meteors, for example, to estimate the spatial correlation of the mesospheric wind in this direction. I can use those two to estimate the spatial correlation at this length scale and that length scale, right? So if we have 100,000 meteors, we have a lot of pairs that we can use. Of course, there are correlations within them, and that's really a little bit of a topic of future study, but we can do a lot. Here are some histograms of how many measurement pairs we can form. So this is temporal distance and this is spatial distance. This is spatial horizontal distance, and I'm assuming that I'm forcing the meteors to be within a 1 kilometer altitude range. So obviously we have a lot of meteors which are in the same place with 0 time delay because it's the same meteor, right? Let's say 10-second time difference and let's say 100-second time difference and 10-kilometer spatial difference. We already have, close to 1,000 meteors at this altitude range. And here, if we are considering, 10-hour time delay and 100-kilometer horizontal separation, we have almost a million pairs that we can form. So we have a lot of measurement pairs that we can use to get statistics, to get different lags of the correlation functions. With 100,000 meters, you can already do a better job with a mean wind. Here's a mean wind done with 30-minute time resolution and 1 kilometer altitude resolution. No overlap between the bins. Here's a 4-hour average mean wind. So this is meridional and zonal wind. Same data, but with 4-hour binning. If I subtract the 4-hour mean wind from the half an hour mean wind, the residuals show me these kind of oscillations, which are approximately 3 hours, and they have a different vertical wavelength than the tidal waves have. So we think this is real. I have not seen it before. I think Markus Rapp has seen something like this with Marcy. But anyway, this is interesting. And to validate our method, I compared the mean wind. So from the mean wind, you can get the zero lag of the correlation function with the same binning. So I compared my method, which I called the wind field correlation function inversion, with the well-known, well-vetted technique for mean wind estimation, and I estimated the UU, VV, and UV, the horizontal correlation functions, and with the same data, I get pretty much the same result, even though these two methods are completely different. Here's the kinetic energy, by the way, as a function of time and altitude. Okay, so and if I do the scatter plots show that it's a one-to-one relationship, so the method is unbiased, which is good. So we can then go forward and do things that we cannot do with mean wind estimation. So first of all, one thing that you can do is you can estimate temporal correlations. So this is a temporal autocorrelation function of the zonal and meridional wind, and you can see that it has a 12-hour cycle. This is time on the x-axis, and y-axis is correlation. If I look at the sub-4-hour fluctuating component of the wind, I can see this kind of damped oscillation, which pretty much has that 3-hour period. And if I look at sub-1 hour the fluctuating component, I can see this kind of a damped autocorrelation function. And I can already tell from this how much kinetic energy there is in these different wave modes. So about up to 20% of the energy is in this sub-4-hour component of the total wind energy. This light line here, these dark lines, these are large scale. So I did the binning in such a way that I could have meteors anywhere in 500 kilometer horizontal distance. The light line, I forced them to be within 100 kilometer radius, so that I can measure how much more energy is there when I consider small scales compared to large scales. And this tells me that there's a little bit more kinetic energy that decorrelates on larger scales. So this is really a all singing, all dancing measure of kinetic energy at the temporal scales and also spatial scales. The correlation functions are related to something called the structure function. So that's the definition of structure function. Kolmogorov already used it in his 1941 paper to derive the two-thirds law. If this is to the second power, and these are means, you can relate the structure function to the zero lag of the correlation functions and the minus the 2 times the cross correlation function at a lag of tau and s.
3 minutes.
Okay, I'm almost there. Okay, so why is the structure function important? Well, first of all, we now know how to estimate these correlation functions with different spatial and temporal lags, which we haven't had before. If we can do this now, we can go back to the structure function, and we can actually relate what we measured into the structure function. So we now have a structure function of the mesospheric wind at different temporal and spatial scales. Structure function is useful because, maybe I'm not a good mathematician, but I'm not very good at Fourier transforming a spectrum of this form. I think it's because if k is 0, I get into problems. But with the structure function, you don't actually have to, if you have a spectral model which is a power law, you don't have to Fourier transform. You can, if your structure function is a power law, p minus 1, that corresponds to a spectral model of k to minus p. So all we need to do is we need to look at this structure function to see what the spectral index is. With no Fourier transforming involved, no windowing, no practical nuisances that are involved with spectral analysis come into play here. And so here's an example of a horizontal autocorrelation function of a fluctuating component of the wind. This is zonal and meridional wind. You can see that and this is the lag. So this is horizontal lag between 0 and 500 kilometers with 25 kilometer lag spacing. You can see that or I think it was 12.5 kilometer lag spacing. You can see that the wind decorrelates as a function of distance. And if I now convert this correlation function into a structure function, I see and I plot it on a log-log scale. The error bars are large, so it's not statistically significant, but the mean value follows the 2/3 power law. So this indicates that in the horizontal direction, the mesospheric wind is in agreement with the Kolmogorov theory for turbulence, a distribution of kinetic energy in turbulence. How many minutes do I have? Is it done?
1 more minute.
We have lunch next, so I should be actually maybe I will skip this. Questions? So anyway, we've done, maybe the last thing I want to say is that I've been privileged to be able to work with IAP and participate in all of these different advancement in the technology of meteor radar technology. So I think we have, IAP in my opinion is the world leading institute for doing wind measurements with meteor radars, in addition to LiDARs as well and modeling. So that's about it.
Thank you. Couple of short questions.